All right. Last time I was here was about 4.5 years ago, so it's great to be back. I wish I came here more often, but and so there's been, that was a few years after my postdoc, and now there's been a lot more work happen, and I'm trying to build upon. Some of what I'm showing today builds on what people might have seen back then. Probably very few of you were here back then, 4.5 years ago. But so the general topic area, I'm going to have two presentations, one on storm protection benefits and century scale trends of Jamaica Bay marshes for about 20 minutes, and then latter parts on nature-based flood and hypoxia mitigation for an urbanized estuary. And so this is Jamaica Bay marshes with New York City in the background. It's the one region in New York City which it's kind of like the Meadowlands. It's a place that has a lot of open space, a lot of open water, and historically has had a big decline in its wetlands, even more so than the Meadowlands. All right, so first my co-conspirators in this work, the first half of my talk are Eric Sanderson, who you might know from the Mannahatta Project, mapping historical landscapes. Reza Marsuli, who's now, that's not true, he's not at Princeton now, he's got a tenure track position at Stevens. He was a postdoc with me back then. Hongqing Wang, Jim Chen, and Kaylin Hu are at Louisiana State University. And I'll summarize some of their work that I collaborated on with them. This is funded by NOAA and National Park Service post-Sandy funding. So why study Jamaica Bay? Why would I focus on Jamaica Bay, this one part of New York City? New York City shown here. Of course, with most New York City maps, there's no such place as New Jersey. You might know it doesn't exist over here, forgotten. Jamaica Bay is this one area of the city which is really has a lot of population. This is population density shaded in areas below 5 meters above sea level. So it's just shading the population density in areas within sort of potential areas of flooding. It's not real high population density. It's sort of like moderate urban population density, unlike Manhattan. But there's, it's the place where there's the most vulnerability, people in flood zones. And then the thing that always excited me, right when I started at Stevens, modeling, having models of the New York City region, is it's an area that has about 10 kilometers across it that lost all its wetlands. So it's a really interesting place to look at the wetlands and what protections they might provide if they were restored. That's what inspired me at first, but it's not really where I've gone with this work in the long run, as I'll explain. We're looking more at other ideas. But it's also very representative as an urbanized estuary, and so I want to think more broadly than Jamaica Bay. It's an urbanized estuary. So the questions I'm addressing in part one are, what are the physical benefits of marshes in storms for an urbanized estuary like Jamaica Bay? The methods I'll use are modeling, and I'm going to be pretty brief in summarizing some papers that we published, modeling wetland mitigation of surge, waves, and erosion. Second, how has the bay's landscape changed over the centuries, over 2 centuries of time? And we've done landscape reconstruction for the 1800s and present. We've created models of the estuary for the 1800s and a model of the estuary for the present day in terms of flooding, mainly focused on flooding. And then also modeling tides in the intertidal areas and how much the intertidal areas have changed in addition to the wetlands. The wetlands have been spoken of again and again with Jamaica Bay, and there's good estimates of how much the wetlands have degraded or disappeared. But nobody has published anything explaining how much intertidal zones have disappeared from the bay. But that's something that's also been a really large change. And then lastly, what will be the fate of Jamaica Bay marshes? And I'm just going to reflect on some sort of simplistic marsh elevation modeling that we did, and on the sediment budget. And so we're modeling tides in that case also, and looking at how the tides and sea level rise would drive disappearance of marshes. And I'll reflect on the sediment budget of the bay and some related topics there that could influence marsh sustainability or resilience. So first, I'm just going to review some points that I actually did present 4 years ago here. In multiple studies, we found that marshes don't reduce storm surge for the communities around Jamaica Bay. And that's because there's these it's an urban estuary, there's deep shipping channels around the marshes. And so there's neighborhoods basically that are on top of landfill and where industry traditionally was. And that's where neighborhoods are being placed in many cities nowadays that don't have the small infrastructure and warehousing and shipping. The shipping port moved to Newark and Elizabeth. And so all these neighborhoods around New York City are being developed there's neighborhoods developing on these former industrial sites. And so the deep shipping channels go around the marshes. There's no longer any fringing wetlands. And so if we restore as much as we want to restore marshes in the middle of Jamaica Bay, the water's just going around them and taking these low frictional pathways and not having to pass over them. So this was shown in 3 different sets of studies. First for New York City, consulting firm, I was in collaboration with this, ran our AdCirc. We found that the marshes didn't reduce flooding significantly. Then Reza Marsuli and myself also 2D modeling for a paper in 2015, and then, like I said, Reza Marsuli and myself 2016 with 3-dimensional modeling that included the 3-dimensional effects of wetlands on currents. So we've kind of tried that one in many ways. I think now nobody, like on the Corps of Engineers boat tour I was on the other day, they no longer, after maybe 5 years of hitting them with this news, they finally don't say that marshes stop storm surge in Jamaica Bay. So we've had some influence on that discussion. And I think that's really a useful thing and important that people don't get fooled. Many other places, marshes are very protective. And also marshes have many other co-benefits other than storm surge mitigation. And so that's some of those physical benefits I'll talk about next. Like I said, here's Jamaica Bay. With the marshes were historically, and there's a few left in the middle of the bay. And you have these 10-meter deep, kilometer wide right here, shipping channels going around the perimeter of the bay like a moat. And so there's very low friction. The water just goes around the marshes. So if you want to keep that, if you want to get rid of the shipping channel, maybe you can improve your marshes and they could play a role. But with a deep shipping channel that they won't give up, the marshes in the center of the bay don't help reduce storm surge. So what we have shown, however, is that marshes reduce wave heights and erosion during storms in Jamaica Bay. So there are benefits, and the Corps of Engineers knows this. They've also had similar research to this. This is a study on wave attenuation, which Reza led. We developed wave model and also wave model vegetation impacts with George Malore from Princeton. And so a wave model was used to quantify storm wave height reductions, and I'll show some results in the next slide for this. This is kind of an overview. We validated using data from laboratory scale experiments, so it wasn't validated in the field. That's somewhat important. We had a 5-meter resolution model grid on this area of marshes inside Jamaica Bay, and we applied it to study waves during west wind events and also during storms. So winter storm and hurricane wind wave conditions. And we also looked at whether or not there's just islands in place which break the waves, or whether there's islands in place with wetlands on top of the islands. But the wetlands actually hold the islands in place, so they're somewhat integrated in with the substrate. So here's this domain. It's just a small domain. There's a neighborhood here with some very outspoken advocates who are very involved from the Jamaica Bay Eco Watchers organization. They're very involved in public policy and have lots of connections, so we figured they're one place where there's real danger of wave impacts. They're basically homes on docks and very low-lying neighborhood called Broad Channel, New York City. And so here's the transect of the wave height going from the far left side of the red box to the far right side where the neighborhood is, past these wetlands. And so there already have been efforts at restoring these wetlands, and so we're kind of contributing to the conversation about those restoration efforts. Here's the substrate elevation and the areas that have wetlands, not to scale actually. We did wetland experiments with 1-foot high Spartina and 2-foot high Spartina, mimicking different seasons. And we found that there's this big reduction, largely due to the substrate breaking waves, but also when you have higher Spartina, it also improves the reduction in wave height more, but the end result at the neighborhood doesn't really care about the Spartina, it just cares about the wave breaking on shallow substrate during a storm, in this case. And we also, this was just for a winter storm scenario. We also simulated a storm event, like a hurricane event, and found similar results. But yeah, the bottom line is you don't have the substrate if you don't have root systems that hold it in place. So either way, it's the wetlands that are contributing to this reduction in waves. So that was published in 2017, Journal of Geophysical Research. Then the other work I was involved with relating to this topic was on morphology change during Hurricane Sandy, and also simulating a whole year of conditions and looking at longer-term processes of erosion and deposition in the bay. The Delft 3D model was used in this work, led by Jim Chen and Kailin Hu and Hongqing Wang from USGS. They're both from LSU. So it was a hydrodynamic wave sediment transport morphology model. So the morphology can evolve, the depths, the bathymetry can evolve during the simulation. And And we examined the effects of Hurricane Sandy at up to 10-meter resolution in this study. Observations were used to evaluate the model, including marsh elevation change from surface elevation tables and feldspar marker horizons, and also USGS water level measurements were made. And then one thing that was great about the validation was there's a pond called, here, this west pond here. This pond had a breach, and you can see it here in this satellite data from right after Sandy. That breach was reproduced by the model just naturally. It just happened to happen in the same place. So that's a real good sign that the model's capturing the actual processes, the erosional processes that occurred during Hurricane Sandy in this study. So that was somewhat confidence building. So that, again, to get your bearings, is in this region of the bay where that breach occurred. So this is some results. One thing I'll note first is marsh islands are surrounded with magenta lines. These are the different marsh islands of the bay that were of particular interest in this study. On the left side, it shows the actual deposition in reds, yellowish to red, and erosion. This is the net change in sediment deposition during the storm. And so you see some deep area. This is a deeper area of the bay, a borrow pit where they dug out to build JFK Airport. It's got maybe a warmer color. Some of these marsh island areas have more of a blue color, but it's all pretty subtle. So the net deposition and erosion. Over here, it just shades it in terms of white being sort of near zero, erosion being red, deposition being green. And you really see these sharp gradients where there could be, and it's wave driven largely why you have these sharp gradients. There's wave breaking eroding a marsh edge really badly, stirring up new sediment and putting it on top of the marsh. So you get these real sharp differences, and over short distances you'll get erosion and deposition. So Western Bay marshes on average were sediment sources. So this is the Western Bay over here, and erosional. The Eastern Bay marshes, this is one of the more healthy marshes near JFK Airport's runways over here, and they were sediment sinks more often, net deposition, but you really see it's much more complex than being deposition everywhere. There's a lot of erosional locations also mixed in. The bay imported sediment during Hurricane Sandy, but most of the imported sediment, according to the model, of course this is all based on the model, was deposited in deep channels and bay bottoms like this bay here, these deep channels. Without the protection of vegetation, the marsh islands would have experienced more erosion and less accretion in coastal storms in general and during this event. So those are important benefits of the marshes in the bay in terms of holding that substrate in place, reducing wave heights, reducing erosion. All right, so how has the bay's landscape changed over the centuries? This is a project which I think is my proudest accomplishment as a scientist. I just really enjoyed it. It's called AdaptMap. It's a flood mapper, a flood, sea level rise, and adaptation mapper, which has baked into it some pre-computed scenarios of adaptation. And so you can not only look at whether or not, zoom in on your home, your neighborhood, see if you're going to get flooded by sea level rise in the future for different storm intensities, but you can also say, well, let's choose this scenario of adaptation. And there's dynamic modeling behind it, pre-computed with a lot of CPU hours of computing, and it allows someone to see, based on the best model that we had, how much flood risk would change in the future and different return periods, and how much adaptations could help. And so it's kind of a demo. It only has 3 adaptation choices that are pre-baked, and it has 2 historical landscapes, the 1600s and 1800s, but it kind of demonstrates what you could do with more modeling and more time. And so this is like a landing page, and one thing is, and I'll go into more detail, is the history of Jamaica Bay tab. So basically we built these we found historical maps, historical data. Eric Sanderson's well known for Manhattan project, where he mapped out the ecosystems and landscape of Manhattan in the 1600s. So I went to him and said, let's collaborate and model the estuaries of the 1800s. And so there's very good old maps from the 1800s which have not only soundings or maybe lead or something lowered on a string to give depth, but they also have, and you can't see it here, but there's descriptors of what's on the bottom. So they're doing bottom grabs. This is in the 1870s. Bottom grabs, so was it shelly, pebbles, mud, etc. And so there's really detailed information. So we build these land cover maps of 1870s. So a lot of it is natural systems at that point, but there's also farming and other uses at that point already. from development. But there's a lot of marsh areas. The blue areas are all marsh. And then here's the modern day system. And so red is developed. And so you've landfilled a lot of marsh around the edges. And like I said, you've deepened shipping channels a lot. You've also lost a lot of the wetlands. They've decayed away, deteriorated. Here's the DEM of the historical system, very natural, dendritic kind of system with marsh channels and sort of disappearing away into ones that are too fine to fit on our 30-meter model grid. This is the Marsh DEM, actually, the model's grid, basically, as it sees the topography and bathymetry of the system. And then the modern day is all this landfill, JFK Airport, a former airport, and much deeper shipping channels, and going back and forth one time again. So you really see there's a much narrower inlet back then, and now a much wider inlet, which you can imagine this deeper, wider inlet has a big influence on allowing tides into the bay and storm surge into the bay without any frictional effects. And you know, one thing that I've noticed and really been hung up on in the past year, and I really like to study more, is this is 1950 based on NOAA charts, and this is present day. And so there's still this dramatic change going on, even though they're not actually actively doing anything to the system. So it's a change, and sorry I keep switching from feet to meters, but we work with stakeholders a lot in Jamaica Bay because it's got, you know, 2 million people in its watershed. So I will be switching between feet and meters, but you're seeing a difference of, this is intertidal, 0 to 2 meters maybe for this very large area, square kilometers of area, and now it's not intertidal anymore. It's like sometimes more than 6 feet deep. So the center of the bay has had a sedimentary collapse that no one's really documented. Everybody's focused on the footprints of the marshes, but the whole system, sedimentary systems collapsed, according to these maps. So that's a concern if we're going to keep trying to restore marshes, which is a big effort in the bay. One needs to also think about what's below the water surface. So some methods for, so the next thing I'm going to present is I've done tide modeling for the 1870s landscape, the modern day landscape. So trying to look more than just at the wetland loss, but also the intertidal habitat loss and the total intertidal area of the bay and compare it for the two periods. So this is kind of cool. We have not only, you know, when they make a map with that level of detail in the 1870s, they also collected tide data for a month. The only downside is they only collected it during the day and not at night. So it's hard to use with tidal analysis. It's a little more challenging to use these data. But yeah, so it's hand tabulated hourly, or no, actually 10-minute resolution data. So I'm simulating tides with our Stevens estuary and coastal ocean model in two-dimensional modeling, actually. The model grid has 30-meter resolution, and it's the same one used in a prior paper on Jamaica Bay. So we get fairly accurate results modeling the tides in the system. A lot of that's dependent on the larger scale model that we're nested inside, but we've got a good reproduction of the tides for the system. The red dots are observations, the blue is model. And so the historical changes based on this modeling and based on the mapping from the 1870s to the present, and I have a paper that's drafted on this work but not submitted yet. The total marsh habitat area in the bays declined 76%, and similarly the intertidal unvegetated areas, that whole intertidal zone around the marshes has declined by about the same amount, 74%. The deep water habitats increased by, you know, a similar factor, factorially similar. It's 240% increase. So the bay's really been converted into much more of a deep water habitat. And I think this is really typical of urbanized estuaries, and I think it's spreading around the world. Increasingly, estuaries are being converted into ports to this day right now. So what will be the fate of the marshes in the future? Like I said, this is fairly simplistic modeling. It's marsh elevation modeling. Basically, we're not dealing with edge erosion, and that I think is increasingly, I see the conclusion that that's the real problem with the marshes. So we set marshes to exist. We did tidal modeling, and we had an initial landscape, and then we modeled the future with sea level rise, and we look at how the tides change, and we set wetlands to exist between mean sea level and mean higher high water tidal level. And we also have an accretion rate that we apply, and we have marsh collapse. If a marsh goes away due to being drowned, then the substrate drops by, I can't remember, 20 centimeters or something like that. So fairly simple modeling. It does predict a continued loss of the marshes. I always said the cool thing to do here would be to go back in time and see if we can reproduce the historic change of the past. We haven't done that. And And again, this model doesn't include some important processes, but it agrees with other studies, such as with SLAM, that suggests that the marshes will have nowhere to migrate and they'll be disappearing. So, and just reflecting more broadly, what will be the fate of the marshes? I don't have a firm answer on that question. Relative sea level rise at Manhattan is about 4 to 4.5 centimeters per decade right now, if you take the global rate of sea level rise and the land subsidence rate. If anything, we've seen a little bit less than that the past 20 years. A new study by Dorothy Petit at Lamont Doherty just published found that accelerating organic sediment accumulation has outpaced sea level rise. So these marshes are getting enough sedimentation on top of them to survive. But reduced inorganic sediment delivery, that is sand, et cetera, sands, fine sands, leads to there being, this is all organic matter that's landing, organic rich sediment landing on top. So there's structural weakness and edge failure. They're very susceptible to edge failure. The bathymetry shows, as I showed, it shows evidence of morphologic collapse. Just the sedimentary system is out of balance, and you're losing ground, literally. Inorganic sediment supply to the marshes is compromised. Borrow pits are sinks for sediment, we've shown with that modeling. We weren't sure, based on the modeling, if the channels are also sinks or not, because they get stronger currents. The borrow pit's that area that's very stagnant, where they just dug out a huge hole. And intertidal flats are an important but disappearing source of sediments to get washed up onto the marshes. But if they're sinking and disappearing, then there's not much sediment supply from erosion around the marshes to supply them so they can maintain with sea level rise. So if anything, the future of the marsh islands is up to humans. We've seen from everything I've shown you here that humans have really controlled the system in a dramatic way. Right now, they're rebuilding marshes. It's really largely up to humans. We have quantitative evidence that during storms, Jamaica Bay salt marsh islands cannot significantly reduce flooding, but they do reduce wave heights. The substrate's an important part of that. They do locally reduce erosion, enhance deposition. And the marsh islands are surrounded by a collapsing sediment substrate that was intertidal previously and is now subtidal, and it reduces the sediment supply to the marshes. The future of the marsh islands is up to humans. Sea level rise is accelerating, and it's definitely an existential threat to these marshes. Many studies have shown them going away. Inorganic sediment supply is too low. Edge erosion is very common. My recommendation when speaking to the Corps of Engineers and stakeholders around Jamaica Bay is, as they're replenishing these marshes and trying to rebuild marshes, they need to also deal with this larger sedimentary platform that's been sinking and dropping away. And they need to add sand in a larger area around the marshes. And there's plenty of sand available from dredging of New York Harbor, the channel deepening that they've been through. So sand really isn't, there's not a shortage of sand. It comes in pulses when they have big projects. So that's my recommendation for the stakeholders involved in that. So that's the end of the first part of my presentation, and now I'll speak about nature-based flood and hypoxia mitigation for an urbanized estuary. And collaborators in this are from a consulting firm that works with New York City on water quality modeling. So we use the actual water quality oxygen model that New York City bases its decisions on in this project. And that's Jim Fitzpatrick and others at HDR Incorporated. Reza Marsuli was also involved, and Stefan Talka from Portland State has generally just been a collaborator in this work. And this is funded under the National Park Service funding. So the motivation for studying flood mitigation and hypoxia together, water quality and coastal flood mitigation are really two integrally connected topics. And we're learning this right now with the storm surge barrier proposals for New York City, New Jersey. There's a lot of concerns about water quality. If you reduce the storm surge penetration to a city, then you're also potentially reducing the escape of pollutants or eutrophic waters from an urbanized waterway. Moreover, climate change is going to worsen flooding due to sea level rise, and it'll also lower dissolved oxygen concentrations just simply due to warming of the water and the lower solubility of oxygen in water. And something that really motivates me is that there's really been no nature-based solution proposed for urbanized estuaries with these deep shipping channels. So the only solution, the Corps of Engineers keep saying this, the only solution they know of is to build barriers and to have gray infrastructure solutions. Of course, there's retreat, but New York City's not really looking very seriously at retreat right now. And so there's really, and that's a big motivator, and one of the things I'm addressing with some new ideas for flood mitigation in this presentation. So just a brief review, important for this audience with estuary experts, on the physical estuary conditions in Jamaica Bay. So we have, this is all model-based here. It's a model that's been validated with some observations, but I'm just showing the model results for a neap tide. And this is a transect, let's find a map real quick. It's a transect coming into the bay down here and going along the north channel all the way into this borrow pit bay at the back. So it's a north channel transect. And so on neap tide, you have some stratification. It's basically a well-mixed to partially mixed estuary. And so during spring tide, you really hardly have any stratification. Thermal effects sometimes are important, but what I'm showing here is just salinity. But generally, salinity is more in control of the stratification, except in the borrow pit area that's very stagnant. And then a neap tide after a heavy rainstorm, sort of the maximum I would ever see is about a 4 part per thousand or PSU density difference. So this is a histogram of the number of hours per year in a simulation of different amounts of top to bottom density difference or stratification. So typically it's a pretty low stratification in the system. But it does get a mild estuary circulation and shear dispersion induced by this two-layer, a little bit of a weak two-layer flow on neap tides. And typical tidal currents are about 1 meter per second in the inlet and 0.5 meter per second in the bay's main channels. The freshwater, one thing that makes this an urbanized estuary also is it has this very continuous freshwater supply from sewage treatment, which has a great deal of nitrogen added to it. But it's a very continuous freshwater supply. Then there's occasional rain events that that increase it by a factor of 10, but they're short term. And so really it's just got this very continuous, predictable freshwater supply that adds to that estuary flushing and that circulation. All right, so some methods on the water quality side. Here's the 3D, three-dimensional modeling that we're using. Like I said, this is a model, it's called GEM, this grid, and it's used for water quality decisions related to Clean Water Act for New York City. It's used for them evaluating if they should lower their nitrogen inputs, et cetera. And so it's been validated extensively. It got validated in this project additionally using 1995 to 96 extensive data, new data from Bob Chant, temperature and salinity, collected during his National Park Service project, and velocity also. And the two-dimensional modeling that I'll present separately was validated using Hurricane Sandy and 2015 tide simulations. So it's a combination of the 3D modeling that's got detailed processes looking at water quality and oxygen, and then two-dimensional modeling looking at tides and flooding at 30-meter resolution. So water oxygenation, this is a diagram of the model that's used. It's a very tuned and detailed model with 27 state parameters. It's kind of like what you expect for a consulting firm working for a city. It's not an academic model. And that could have the shortcoming of being incorrect when you change the system a lot. So that's one possible shortcoming here. It's a hydrodynamic model. It's got a eutrophication model with the nutrients, sediment flux model. It's also got some specialties like an ova model. The ova are the macroalgae, the large-scale algae that forms on the bed. Benthic algal model and suspension feeder model. And it was validated during the study for 95, 96, and 2015 observations. And it's based on the RCA modeling engine. GEM is just the local application. So the flood assessment methods and mitigation benefit computation methods are from flood simulations for specific storm scenarios, and also a flood hazard assessment, which I published in Journal of Geophysical Research a few years ago, where in that case it was over 1,000 different storms, so trying to look at all possible storms that could affect New York Harbor. Here I'm just simulating a subset of the most common storms that span the whole range of low floods to high floods, from tropical cyclones, extratropical cyclones. And so 80 different historical extratropical storm tide events, and then 64 synthetic hurricane events. We don't have enough hurricanes in this region to really to trust the historical record to tell us about risk. So we do what insurance companies and a lot of scientific researchers are increasingly doing. And we have a synthetic hurricane model. These are just some of the worst cases out of a million-year simulation of today's flood risk. So it's a million of today's years of today's type flood risk. And so these were category 4, not trying to pick on Rutgers or anything with these storm tracks, but these are category 3 and 4 hurricanes making Hurricane Sandy type left turns. And these are like 1 in a million year chance storms. I'm just showing them because it captures the fact that this model includes sort of any kind of hurricane you might imagine based on a model that's created from historical data. And then the end result of that kind of hazard assessment is you have the probability, or flipped over the return period of a different flood height, and you've got an uncertainty. You've got your green line is your winter storms, extratropical cyclones, not a real high-end risk, but the more common events for low return periods, and then the red line is tropical cyclones, which has very rare occurrences, but extreme consequences if you have a severe event. And that's what Sandy showed us, basically, is you can have this rare event that has a much higher flood level than anyone's adapted to. So that gets used on the Jamaica Bay landscape model for 1870s and present day, and I'll show some of those results on how the flood risk has changed. You know, the way that the landscape in the 1870s resisted a flood has really been completely modified. So now I'll talk about some of the adaptation options for Jamaica Bay. One is the storm surge barrier. This is from the Dutch, these two cases. This is from the Thames barrier. And there's really no diagram showing what it would look like, but it's in this area. Floyd Bennett Field is where they proposed to do it. It was sort of accepted by New York City, and it's the tentatively selected plan for a Jamaica Bay study, but now it got wrapped into a larger study called HATS, which is the Harbor and Tributaries Study. In my presentation today, I'm just going to summarize some results from a study that the Corps of Engineers did with New York City Department of Environmental Protection. I'm not going to actually, it's not my own results, so I'll just be brief about that. So I mentioned the Harbor and Tributaries Study of storm surge barriers. That is shown here. This is a map from Harbor and Tributaries Study, which is ongoing right now. The Jamaica Bay barrier got folded into it as a possible part of a larger scale protection system looking at New Jersey and New York. So they're thinking more regionally now. It's a very political hot topic with a lot of interest, a lot of unhappy people that you would be talking about blocking up the Hudson River even partially. And so it's really exciting to be involved in that. I have funding from NOAA to be involved in that for the next year, trying to help improve the science alongside the Corps of Engineers work. So this is just one scenario where there's a barrier at Verrazano Narrows, one at Jamaica Bay, Throgs Neck, and Arthur Kill. Then the other scenario has a barrier that's further offshore from Sandy Hook to Rockaway Peninsula, and also the Throgs Neck barrier. So, and I just wanted to plug that, you know, we getting a little bit off topic here, we co-authored a preliminary study of surge barrier influences on the Hudson River estuary, and there's a seminar this coming Friday from the Hudson River Foundation where I'll be speaking about that work. And like I said, I have a NOAA-funded project for the next year to study storm surge barrier potential impacts on the Hudson. And so the adaptation option, another adaptation option, so that was number one, is storm surge barriers. Another one is wetland restoration. Various proposals have called for restoration to either a 1974 footprint or an 1870s footprint of Jamaica Bay, central area wetlands. So here's one case of restoration to the 1870s footprint, so really taking it all the way if you had the funding and the interest. So you see, you can't really see the substrate change here. It's difficult to tell, but this is land elevation maps that go into the model. And this is land roughness, Manning's End roughness for two-dimensional modeling. So you do see there's a lot more of this lighter blue color, which is a rougher substrate. Interestingly, when you don't resolve buildings and streets in your model, you have a very high roughness for city streets that have buildings. That's just capturing what happens subgrid scale, which is that the water's hitting buildings and it can't go over it. This is a bare earth model. It doesn't see buildings. So what you use with AdCirc or any of these flood models commonly is this really high roughness for urban areas, which is kind of counterintuitive, that they would be protective. I mean, I guess they're getting damaged as they're protecting. But so the center of the bay has more roughness, so that's the big change there. This comes, and so the third option I'll start talking about by introducing it with this diagram that we created for an NSF proposal. The third option looks at changing bathymetry in an estuary. So this nicely summarizes how you have storm surge impinging on an estuary, you have local wind set up, you have the remote storm surge from a storm. Historically, the changes have been sea level rise, small amount of sea level rise. you've had dramatic deepening of many estuaries in the United States. A factor of 2 doubling depths or even 3 is not uncommon. And so you've had a lot of deep dredging. So you have your modern bathymetry, your historical bathymetry. The continental shelf's relatively unchanged. Your wetlands may be landfilled and modified a great deal. So the surface area or tidal flood area may be different. And so there's an equation here. So these are some of the changes you've seen. We've seen in the past century or 150 years, or even 300 years for a city like Boston. They had a lot of landfill back in the 1700s. And so here's an equation that shows that the frictional effect on a tide or on a storm surge is based on a drag coefficient, which is based on the roughness of the substrate, an amplitude of a sea level signal, such as a tide or a surge, divided by the time scale and divided by the water depth. And so the frictional damping depends on the water depth inversely, it depends on the time scale inversely, and the amplitude directly. So if you have so what's important there is if you deepen, then you have less friction effect on it. If you have a fast storm surge pulse from a really strong hurricane, then your frictional effect is stronger for a fast pulse event. And if you have a slow storm surge like Sandy, then friction doesn't really interfere as much. So if you modify the bathymetry, you're having a bigger impact on hurricane storm surge and maybe less of an impact on the slower extratropical cyclone type storm surges. And so the time scale of the tide or of the storm surge really matters a lot too, in addition to the water depth. So here is, so when I run those 144 storms through the model for the 2 different landscapes, 1870s and modern day, or modern day and 1870s, these are the different flood areas that you see here and flood depths in meters. So the 1870s landscape had a much bigger floodplain that the flood spread out through. It also had a real clear damping going through that narrower inlet. So we're learning, a major point of doing this was we want to learn new ideas for nature-based mitigation of urbanized estuary flooding. So the present day landscape amplifies, if anything, it amplifies a storm tide as it comes in. It definitely amplifies the tides. When we look at the tides, they're much bigger in Jamaica Bay than anywhere else around New York Harbor, except for Long Island Sound. And you also aren't allowing the water to spread into the neighborhoods, which is protective, but you have a higher water level. So you're amplifying the water levels instead of damping them. So the idea that came from this is the idea of shallowing, which I did present 4 years ago, I think, in seminar here. Some preliminary thoughts on that. So if you could shallow, one thing that's been proposed before that's not totally harebrained is that you could fill in the borrow pits where they dug out and they have these stagnant areas that are anoxic sometimes. So that's something that's been on the table before but resisted by the local population as being, for various concerns, which I'll discuss in a minute. But this new proposal that we came up with was that you would shallow the whole bay either in a smaller amount than this or even to this extreme where you taper the shallowing all the way deep into the bay to where it's about 1 meter deep in the back of the bay, 5 meters deep in the inlet, and so you're shallowing the entire bay. And so the substrate also is changed in that I assumed, and this made a small influence on the results, but I did assume that the bottom gets rougher. When you have stronger currents and you have sediment that's more in equilibrium and being eroded constantly, then it tends to have sand waves and have more resistance and more of a frictional impact. So I did roughen the Manning's number a small amount, so we have a slightly rougher substrate in addition to this deeper. But the influence that had on the results is more something like a 10% kind of influence, not a big influence. But I think it's realistic. So the results on flooding, well, no, actually the results on water quality and flooding, first with storm surge barrier, is that a surge barrier seawall system eliminates all flooding during storms up to about the 100-year flood and with waves on top of that flood. Reflection causes higher water levels just outside the barrier around Coney Island. So there's a reflection issue when you have a barrier. But that can be mitigated. It's only something like a foot of extra flooding at Coney Island offshore of the barrier. And that can be mitigated. The Corps is fine with that. It can be mitigated with some higher seawalls around Coney Island. Not necessarily a big deal, but and so it's not really a long-term solution for sea level rise, however. Sea level rise is still allowed into the bay with the tides. You can only close this barrier when there's severe storms, and you can't close it all the time and prevent sea level rise from causing tidal flooding. So there's no effect, or the effect on water quality is based on this New York City DEP study, There's a small effect on year-round biogeochemistry. Modestly worsens oxygen and pathogens level if you have a 25-year rain flood when there's a storm surge and they have to close the barrier. And then lastly, it badly worsens oxygen and pathogen levels if you had a sort of unusual hypothetical event where the barrier gates are closed for 4 days and there's a lot of rain spilling combined sewage overflows and such. So for the most part, it's not severe negative effects. The flushing of the bay, even when the gates are open, is fairly good. And so the impact on general water quality isn't very severe. So that's what allowed the Corps and New York City to conclude that this was the best solution for Jamaica Bay at the time, that a surge barrier was the best solution. Because it can stop storm surges and it didn't have severe water quality impacts. So the results of the wetland modeling of flooding are shown here. So the wetland restoration, so Hurricane Sandy on the left column, Category 3 hurricane from 1821 on the right column. So I'm not showing you the full risk assessment results. I'm just showing, because we didn't do that for wetland restoration. I'm just showing a slow moving storm surge and a very rapid Category 3 hurricane storm surge and what occurred. So this is the reduction in flood height on the far right. Generally, it's near zero in all these cases. And so at the bottom, on the top row, it's wetland restoration. The bottom row is extreme shallowing of the bay. This is what was evaluated in 2015 Journal of Marine Science and Engineering paper, the first thing that we did when looking at shallowing. So what you see is there's not much impact from wetlands on the flooding, on the water levels. There is a reflection problem, actually. These red dots are where you have new flooding. Black dots are where you have prevented flooding. So there's really, on balance, there's no reduction in flooding. There's new places with flooding offsetting the areas that were protected from flooding for that hurricane. For extreme shallowing, you have a modest reduction of about 1/2 meter or 40 centimeters for the Sandy event. A lot of areas, the black dots are prevented from getting wet. And then in terms of a really rapid fire, like I said, there's stronger frictional effects when you have a really fast pulse storm surge. So there's protection of about 1 meter reduction in the 1821 hurricane storm tide, in a lot of areas that are prevented from flooding, including most of Rockaway Peninsula. But there is some reflection, a little bit of a reflection problem in that case. So what we've developed is this was the first paper from 2015. We developed a way to reduce a storm surge that doesn't reflect the storm surge. So it's got sort of an artful aspect to it that it's more dissipating the storm surge instead of reflecting it elsewhere. And it's fairly effective, but it's very extreme. You're not likely to shallow this bay to 2 meters depth. So this was an initial look that we had that was just kind of probing the leverage you have with these different methods. So in terms of wetlands and hypoxia, this is still actually ongoing modeling that I haven't finished yet. The preliminary evidence suggests that the restoration of all the wetlands in the center of the bay will have a minor impact on hypoxia in the bay because the water doesn't have to flow through those wetlands. The residence time of stagnant areas like Grassy Bay actually gets increased if you have more wetlands in the center of the bay because it actually reduces flushing of the back of the bay, and that can be a negative. But denitrification in marsh sediments can be helpful in improving the oxygenation of the bay, but it's likely to be small relative to the massive anthropogenic fluxes of nitrogen into the bay. Like I said, that's still, we have modeling going on to try to quantify that right now. And so going to this other idea of sedimentary restoration, adding sand into the bay, this new idea, it has the potential to both substantially mitigate flooding, as shown by that extreme experiment with 2 meter depths, and also it can improve water quality. So the results on flooding, when I run the full risk assessment with that tapered shallowing that I showed, are that relative to a future wetland action, there's about a 50% reduction in flood area in 2055 for a 100-year flood. So it doesn't stop flooding, but it can reduce flooding. So that's a positive. And the Corps of Engineers hasn't really evaluated this, and they really need to because they don't think they have a solution, nature-based solution for flooding in an urbanized estuary, but we've really demonstrated it and we're publishing this work. In terms of oxygen, you can imagine that filling a deep borrow pit that's stagnant and gets anoxic, if you shallow that, then you're going to have much more vertical mixing and aeration from the atmosphere into a 1 meter deep water column. So that's a no-brainer. But in general, and it'd be good to separate that out, but so far what we've done is just evaluate this whole concept of tapered shallowing of the bay. And what we see in terms of summertime maximum chlorophyll is not a huge change, but if anything more chlorophyll in the bay in these areas in the North Channel, then, oh, and by the way, so on the left it's current without action, middle column is future without action, 2065, and right side is 2065 recontouring or sediment, adding sand into the bay. So it's something that I wouldn't recommend doing in like 5-year period. It's something that we really I look at as something that could be done over decades. So we're looking only at the future with the modifications, and we see more chlorophyll. We see a dramatic reduction in hypoxia. Well, what's mapped here is the minimum DO in summertime, and it's much higher and well oxygenated compared to the minimum DO in the present day in the future without action. So we're reducing, at 2065, we're reducing hypoxic water volume in the bay by 81%. So we're substantially mitigating flooding, not completely, and we're also reducing hypoxia in the bay, which the city spends hundreds of millions of dollars on every year. So that's another possible value or justification. So just to talk more broadly about this idea, the public perception, this shallowing idea was partially accepted into a study that just got published in a RAND report that was a very interactive process with New York City, with stakeholders, sort of guided by the stakeholders, National Park Service. And they allowed us to study the shallowing concept, also a narrowing of the inlet concept, and these ideas, but there's some stakeholders who really don't like it. They don't want there to be big changes to the bay. They're willing to allow a storm surge barrier in some cases, which I think is an equally dramatic change. But they're resistant to shallowing the shipping channels. It was not accepted in the end, so we were allowed to quantify it and do this modeling, but then at the end of the study they said no to the shallowing, but they did say you can have the narrowing of the inlet. So that was something we invented that's a nature-based approach, which actually got accepted as an alternative to the storm surge barrier in the final report. So that's kind of a victory, but the narrowing of the inlet doesn't really help nearly as much unless you also shallow the substrate and really choke the inlet more. So the realism of it is that it could be performed at some level over decades. Minor sand restoration is already occurring when they do the wetland restoration. They're putting sand from harbor dredging, clean sand, onto those wetlands. Dredged sand and gravel is available from New York Harbor on a regular, every few years there's projects that provide it. The broader applicability is that dredge systems like Passaic River have naturally filled on their own when the dredging is not maintained regularly. And the Mississippi River Gulf outlet was actually blocked by the Corps of Engineers when it was determined that it probably increased the flooding during Hurricane Katrina. So it's not a totally crazy idea to undo a dredged shipping channel. A key issue here in Jamaica Bay is there's about 3 deep-holed ship passages per day only. So it was envisioned historically that it would become the port of New York and New Jersey, and in the end it just didn't make sense to have the port there. It got put in Newark Elizabeth. And so really there's almost no shipping traffic. One of the important uses though is sewage sludge, and so there's certain uses that are really important. So they're not going to turn off all the shipping, but and you can also do you can do a lesser shallowing and still reduce flooding and improve hypoxia by filling the borrow pits, for example. So the broader applicability is there, and I think that it's an idea that could be used elsewhere, even if it's not accepted here. So my final conclusions: nature-based flood and hypoxia mitigation approaches were tested for Jamaica Bay. The wetlands have a minimal impact on flooding, though they can mitigate erosion and waves. They likely have a small impact on hypoxia, but the jury's still out and we're still doing that modeling. Sedimentary restoration, adding sand into the bay from either offshore or from harbor projects. It can reduce flooding substantially, but not completely. It can also sharply reduce hypoxia in the bay. We're evaluating gradations of that sort of sedimentary restoration that are lesser than not as extreme, that could be used more as a pilot project to better understand the processes and what occurs to the sediment after you put it in the bay. And lastly, we have an ecosystem service valuation study underway right now that's nearing an end, where we're looking at these different options from the broader palette of different ecosystem services like oxygen regulation. And that's it. So I welcome questions. Thank you. Yeah, we're warming the water, we're warming the atmospheric boundary conditions. Yeah, but it's very simple. We're just applying the atmospheric warming to the water. So we didn't go further to find, nested inside ocean condition for the future.
Do you have a sense of relative
Well, I know when they look to reduce nitrogen inputs, which is what they're already trying to do all the time, they spend hundreds of millions of dollars, right? So that's an expensive way to go. Shallowing the bay to that extreme costs order of $1 billion. So you know, they're all things that we haven't gotten into that level of depth, and we still have to publish some of the adaptation work looking at shallowing. We've done benefit cost analysis for storm damages, and found a pretty good benefit cost ratio, but you know, in terms of reducing nitrogen, it's very expensive. So that's exactly what I would like to get at with the ecosystem service project, but I don't think we're getting that far, unfortunately. I don't have good control over this biogeochemical model. It's run by a consulting firm, and it's a challenge for me to run it. So, but I would love to run more experiments with it and understand how much filling the borrow pit reduces hypoxia versus shallowing the whole bay. You know, is it mostly just from eliminating these deep holes, you know, non-circulating holes? Go ahead.
Nitrogen reduction strategies advanced through treatment or running a discharge offshore?
The expensive one that I'm thinking of that was, I think, $400 million was building a storage tank to capture a CSO and not let it go and hold on to it till you have capacity to treat it at Paradigate Basin. Yeah. So, but there's a lot of different, you know, projects. I think they're also, I'm not sure that all the aspects of their nitrogen reduction programs, but I think improving treatment's definitely part of it too. Yeah. So putting it offshore has been ruled out. That was studied with this water quality model, I think, and huh? Good question. I don't remember. I know it got ruled out, and I can't remember the reasoning, but yeah. Yeah, I know they did it in Boston, right? They put it offshore for Boston. Yeah. Yeah. It might have to do with coastal tourism and business. You know, it just is how it is, and changing things always leads to big opposition. But I don't know. It's a good question. Yep, Josh.
Well, are those channels still actively dredged and maintained?
Only at the inlet. So they don't really sediment in very quickly. You can still see in the side scan sonar, you can still see these huge dredge patterns from when they dug it out. So it's not sedimenting in very quickly.
So even if left alone, it wouldn't just naturally?
It's like a centimeter per year, I think, is what somebody estimated. So it's pretty slow. They don't need to dredge them constantly, and yeah, they don't. And even if they did, they probably wouldn't, because they apportion money to where there's a lot of use. And I just heard the dredging operator, I was on a Corps of Engineers tour the other day, and that's what he said. He said, you know, this wouldn't be a priority because it's so infrequently used. But yeah, these are like kilometer wide, 10-meter deep shipping channels. The permitted depth of the project is 20 feet mean lower low water, so it's like 6-7 meters. And so how they get to be, you know, they're 10 meters deep. So there's a lot of uselessness to this. So if one thing that I found eliminates a 10-year flood, which floods about 50,000 people, is just to shallow the bay to that depth, 20 feet mean lower low water, and that shouldn't piss off too many stakeholders. But their fears, I didn't mention, their fear with putting sand in the bay is, well, you're going to give us polluted sediment, because there's a history of them wanting to dump polluted sediment in that borrow pit. But also that it'll reduce the striped bass fishing, which is, you know, they think that they like the deep holes in the borrow pits because the cool water that resides there, they'll hang around nearby to cool off or something. So that's a pretty legitimate concern. There's probably 20 people who make a living off fishing striped bass in the bay. I mean, it's such a minor localized thing compared to billions of dollars of money being spent. So, but they have very strong political power. So that's those are their main concerns, those two. Go ahead.
The search bay, I mean, I would assume it's not one span, right? There will be some piers in between. I guess if you look into the restriction, I know the search bay will be open.
Yep.
You know, the normal town will be open,
yep.
But you only close it during the search. But regular town, I assume there will be some restriction to the regular pipe.
Yep, and so that is, so what we studied was what happens when it's open. Take me a minute. So you do see on here what they thought, you know, this is really preliminary. They weren't even sure where they were going to put it, but these are supposed to be gates, those little bulbs. So you're only going to have about a third of it open. And they found that it didn't reduce the tidal flushing of the bay a lot. So But yeah, so those are gates that are open, and the rest of it's in place, always. So when it's open, the goal is to not significantly reduce flushing, and I think they found that it had a pretty minor impact on the flushing of the bay.
I guess it's
Yeah.
main channel, the tidal, major tidal exchange, right? That's the way it would be open.
Yeah, that's where it is. And one part of it is that it's deeper at these, it's sort of deep right in the middle here. It's at its deepest point. It's just very deep. But yeah, I mean, it seems a little surprising that you could block up that much, these flat parts, 2/3 blocked, and it still wouldn't change the circulation. So, but this is all fairly preliminary, and they were going to do more detailed modeling as a next step, but now it's been absorbed into this larger study of the whole region. So they never got there. Thank you.